Oh, you want to clip me? Okay, now we can have a talk. Defining causality is hard. And people have been trying for millennia. And let me distinguish two kinds of causality. What philosophers call type causality, which is like smoking causes cancer, and what philosophers call token causality or actual causality. The fact that Willard smoked for 30 years caused him to get cancer. So type causality looks at, generic statements, statistical statements you can make, causal statements. Actual causality looks at particular individual statements. I'll be more interested in the latter. So let me give you an example to distinguish them. So you can say, look, it was pouring rain last night, and it's true that I was drunk, but the cause of the accident was the faulty brakes. Now, as far as type causality goes, well, drunk driving causes accidents, and lousy weather causes accidents. But I want to say in this particular case, it wasn't the fact that I was drunk. I drive great when I'm drunk. It wasn't the fact that the weather was bad. In this case, the problem was the faulty brakes. So I think we all have an intuition for what that means, but making that precise turns out to be really hard. So look, these issues come up in the law, they come up in medicine, they come up in history and science. So the question is, what does it mean for A to be a cause of B? And as I say, people have been trying for literally millennia to define this. The modern view arguably dates back to the philosopher David Hume, which is almost 300 years now. And the recent trend has been to use counterfactuals to define causality. Now, a counterfactual is a statement that's counter to fact. That's why it's a counterfactual. So you want to say, if A had not happened, A did happen, but suppose it didn't happen, counter to fact, then B would have happened. And the intuition, which is certainly what's used in the law, is that there's this notion of but-for causality. A is a cause of B. If A hadn't happened, then B wouldn't have happened. So, sorry, Raphael, I punched Raphael, he fell down. And I want to say, my punch was the cause of him falling down. If I had not punched him, he would not have fallen, okay? So that's called but-for causality. And that is the standard definition of causality used in the law. Unfortunately for the law, and fortunately for me, otherwise I wouldn't have a paper to write, but-for causality is not good enough to capture all of causality. So I want to say, if we have but-for causality, then we have causality. But there are cases of causality that are not but-for causality. Let me explain. So trying to make it precise turns out to be hard. And so here's an example, and I'll come back to this. This is an example that goes back to David Lewis. So suppose Susie and Billy both pick up rocks and throw it at a ball. Susie throws a little bit harder, or a millisecond earlier. Susie's rock hits the bottle. The bottle shatters. We can see that Billy's rock would have hit the bottle if Susie's rock hadn't hit it. So I like to say, first of all, Susie's rock is the cause of the bottle shattering. I think most of us would say that. But if Susie had not thrown her rock, Billy's rock would have hit the bottle, and the bottle would have shattered anyway. So we don't have but-for causality. And there are, lots of other cases like this. Does that make sense? So I'd like to say we have causality here. We don't have but-for causality. So how can we define causality? What is it? And as I say, there have been many attempts in the literature. I gave a definition with Udapel that appeared, 20 years ago. Now, the trouble is, I'm a theoretician. My back, I have a PhD in math. I wish I could prove a theorem that says we gave a definition. Theorem, it's the right definition. Now, it's not that I tried to prove this theorem and failed. It's that I don't even know how to state the theorem. what does it mean that it's the right definition? So you can show it has certain properties, but how do you prove that it's right? And what has been done traditionally in the philosophy literature, which is unfortunately what Yuda and I had to do as well, is there are now at this point literally hundreds and hundreds of examples created by the philosophers to shoot down other definitions. So people have been trying to define causality for, decades in the philosophy literature, and the philosophers, that's what they do. They come up with examples to show, oh, he thought he had a definition, it failed. Here's an example showing it failed. So the way you show that your definition is good is by showing I can deal with all the examples in the literature. Now, the trouble with that approach is that once people say, oh, you can deal with all the examples of literature, all of a sudden you're walking around with a big target on your t-shirt because now they're going to try to shoot down your definition. And sure enough, after Yuda and I gave our definition in 2001, actually Yuda's student found a counterexample that Yuda and I agreed was a counterexample. So we fixed up our definition and came up with what we thought was a better definition in 2005. And then 10 years later, I came up with what I thought was yet another improvement. There's a whole story behind this. And that's the definition I'll mainly be talking about today. But again, I have no way of showing that somebody in the audience here won't come up with a counterexample tomorrow to this definition. Michal. Okay, what does it mean to have a counterexample? I was just about to say. So basically, a counterexample is an example where all of us have a strong intuition that it's an example where we ought to say A is a cause of B, the definition doesn't, or vice versa. We all agree that A shouldn't be called the cause of B, whereas the definition says it is. So it is the case, I think, that we all have strong intuitions about causality. So a counterexample, and that was the case when I said that Yuda's student came up with a counterexample. He came up with an example where Yuda and I looked at it and said, our definition says A is a cause of B, and we don't think it should be, right? So, and that we have intuitions. It's a counterexample if it breaks the intuitions. I wish I could do better. So in this case, why would we call Susie's throw a cause? And the intuition that we're going to try to capture is, given that Billy actually didn't hit the bottle, in fact, if Susie hadn't thrown, then the bottle wouldn't have shattered. So notice the move that I'm making here. If I just say if Susie hadn't thrown the bottle would have shattered. Billy's rock would have hit the bottle. But now I'm saying, let's keep fixed the fact that Billy, in fact, didn't hit the bottle. Keeping that fact fixed, then if Susie didn't throw, the bottle wouldn't have shattered. So it's sort of like but-for causality, but I get to keep some stuff fixed. That's going to be the idea. So hang on to that. I'm going to make that precise. And why isn't Billy's throw also a cause? Well, as my kids would say, duh, his rock didn't hit the bottle. And we need to capture that too. So, all right, let me be a little bit formal. I promise this is meant to be a talk intended for a wide audience. There's not a lot of formality. So I think you can follow even without the formality, but let's have a little. So the idea, which is something that Yuda's been pushing for a while, is to describe the world in terms of a bunch of variables. And the variables can affect each other, and this effect is modeled by what are called structural equations. So this is called a structural equations model. And it's going to be useful to split the variables into two flavors, what we call the exogenous variables. Their values are determined outside the model. I'll give examples. I think this will be quite clear. And endogenous variables, and the values of the endogenous variables are determined by other variables. So formally, for those of you who know, the way to think about this is, how many people here know what Bayesian networks are? Quite a few of you. So think of a Bayesian network. Think of it, we have a directed acyclic graph. If you don't know, don't worry about it. In a Bayesian network, each variable is associated with a node, and we have what's called the conditional probability table that gives you the probability of that node conditional on the values of its parents. Here we're going to have the same kind of an idea, but we're going to replace the conditional probability table by an equation. that tells you the value of this variable as a function of the values of its parents. So there's no probability in sight. I'll add probability later, right? So think Bayesian network, but replace the conditional probability tables by equations. So technically we have an equation for each endogenous variable. And I'll say equation, but when I write x equals y plus u, that does not mean y equals x minus u. The way to think about these equations is, let's say this one. If I were to intervene and set y to 3 and set u to 2, then x would be 5. So these to model the effect of interventions. If you can somehow go into the world and force these values, these variables to have certain values, it has an effect on other variables. So forcing y to be 5 is different from the equation that says y equals x minus u. So even though I'm writing equality, think of it more like an assignment statement in a programming language. If I were to assign y to 3 and u to 2, then x would get the value 5. Does that make sense? Again, feel free to ask questions. So again, this is my one formal slide, but if you don't like these formalities, just ignore it. So to formalize this, what I'm particularly interested in is if you look at the second line, that I want to be able to talk about primitive events. I want to be able to say x has value 3. This is the most interesting statement. The way to read this is after I intervene and set the variable capital X to 3, then some statement feebles. Okay, now I have little vector signs over the X. Think of that now as a set of variables. So I'm setting x1 to 3 and x2 to 5 and x3 to 4. So that little vector is meant to say I have a collection of variables, so I can simultaneously set them, close off under conjunction negation. So now a formal model has set, the modeler has to specify what are the exogenous variables? Which variables are going to get their values from outside the model? What are the endogenous variables? Which variables get their values inside the model determined by the equations? And then you have to tell me what the equations are. So this is all part of the modeling. When I give you a model, I have to tell you what the equations are. And people can disagree about what the model is. People can disagree about how they're going to split the world into exogenous and endogenous variables. People can disagree and do disagree on what variable to describe the world. So here I'm making a modeling choice and saying, I'm going to use, I'm trying to describe a medical situation, and I want to say, okay, what are the key features of the situation? Those are the variables. Two different doctors or two different medical researchers could look at the same situation and use totally different variables to describe the world, because they disagree on the important features of the world. This is a really important issue. So I'm assuming that we're given a model, and I'm going to talk about causality relative to that model. But I want to stress that people can disagree about what the right model is. And that turns out to be quite non-trivial because you get different answers in different models. When I'm going to define what it means for A to be a cause of B, the definition is relative to a model. You have a different model, we'll disagree maybe on whether A is a cause of B. Okay, it's all model relative. And so let me explain what does it mean in a model to say that Y is 7? Well, Y is 7. Well, so I'm going to restrict to models that are described by these acyclic networks. So think at the top, I have exogenous variables. They get their values from outside. And then I have all the other variables. For each other variable, not an exogenous variable, I have an equation that will tell me what its value is as a function of its parents. So once I give you the values of the variables at the top, the exogenous variables, that forces the values of everything else. Does that make sense? Because we just have these equations, and you work your way down the graph. There's no cycles. It's an acyclic graph. So once I know the parents, I know the children, and I know their children, I figure out everything. Okay? So when I say Y is 7, I say, okay, the U it's called a context, tells me the values of the exogenous variables. I have a model, and once I know the values of the exogenous variables, that forces everything else. Are we together? So that'll tell me that y is 7. Now, the interesting equation, come back, is what does it mean when I set x to 3, phi is true? Well, setting x to 3 means changing the model. How do I change the model? I used to have an equation for x in the model. If I think of x as an endogenous variable, there's an equation telling me the value of x as a function of its parents. Got that equation. And I replace it by a new equation that says x is 3. I don't care what the parents were. I'm forcing x to be 3. So that gives me a new model that's identical to the model, except I've replaced the equation that determines the value of x by a statement saying x is 3. Are we together? That's just a new model. That model is going to be the model I call m x sub, x gets 3. And then I can determine if phi is true in that new model. So that new model describes the effect of intervening and setting x to 3. It says, forget whatever equation you thought determined x. I'm going to intervene. I'm going to force x to be 3. X is no longer determined by its parents. So now I have a new model, and I can figure out everything else. Again, does that make sense? So that's it. That's all the formality. Let me give you some examples. So imagine we have 2 arsonists who drop matches in different parts of a dry forest, and they start to burn. And imagine 2 scenarios. One I'm going to call the disjunctive scenario, where 1 match would have been enough to start the fire. The forest is really dry. And the second scenario is called the conjunctive scenario. You need both matches to get enough of a fire going to get the forest to burn down. So the way we model that formally is we would have a model, the U at the top, the exogenous variable says, what do these arsonists drop matches? Who knows? That's determined by some exogenous factors. So think of U as determining whether or not the arsonists drop their matches. Now we have 2 variables, ML1 and ML2. ML1 says the first arsonist dropped a match, yes or no. It has values 0 or 1. ML2 also has values 0 or 1, depending on whether the second arsonist dropped a match. And again, it's U that's determining that, but it's not interesting. And finally, I have an equation for the forest burns down. In the disjunctive model, the forest burns down if either ML1 is 1 or ML2 is 1. If either. In the conjunctive model, I just have a different equation that says the forest burns down if both arsonists drop a match. So the difference between the 2 scenarios is captured by the equation for the variable FB, whether it's a disjunction or a conjunction. Again, does that make sense? So that's the way these models work. We have equations. The equations are meant to capture our understanding of how the world works, that it takes 2 matches to start a fire or only 1. And now we want to say, okay, given the model, is it the case that A is a cause of B? Is it the case that the fact that first arsonist dropped a match caused the forest to burn down? Okay. So I'm going to restrict, which certainly follows the philosophy literature, to causes that are, I'm going to ask is A or B the cause of something. But anything can be caused. Any arbitrary Boolean combination of formulas can be caused. So the formal definition of causality has 3 clauses. The first and the third are simple, and the second one I'll leave to the next slide. So I want to ask the question, is the fact that, is A a cause of B? There might be one cause. So the first clause just says, there's no way it's a B unless A and B both happen. We just don't say that in English. I wouldn't say the fact that I punched Raphael caused him to fall, if in fact I didn't punch Raphael and he didn't fall. That's just our understanding. So AC1 just says, if you want to say that x is 3 is a cause of phi, then it has to be the case that x is in fact 3 and phi is true. So again, notice that I talk about A being a cause of B relative to a model. The model tells you what the variables are, what the equations are, and the context. The context tells you what values the exogenous variables have. You might be uncertain about them. There'll be probability coming along later. But this is assuming you know what the model is and what the context is. I'm going to tell you is A a cause of B in that context, in that model. Okay. So AC1 just says there's no way I'm going to say A is a cause of B unless A and B are both true. And AC3, remember X is a conjunction of things. AC3 says you have no irrelevant conjuncts. So if I want to say, okay, the fact that I hit Raphael caused him to fall, well, maybe I also sneezed at the same time. I don't want to say the fact that I hit Raphael and sneezed fall if it's the case that the fact that I hit him. So I don't have the irrelevant conjuncts in A. Throw out all the stuff that you didn't really need for this out. Okay, then there's this AC2. So remember I said I've now written 3 papers with definitions of causality. The definitions all had AC2. So I'm going to give you the AC2 that was in the most recent paper. It looks complicated. All I can tell you is the definition was much. This was a big win. So here's the AC2. And remember, think about the case where I want to say that Susie's throw is a cause of the bottle shattering. And I said, why isn't Billy a cause? Because if you fix Billy at not throwing, not hitting the bottle, because his throw didn't hit the bottle, then I can change Susie. That's what this is going to capture. So there's a set of variables and a setting of the variables in X. So remember, I'm trying to establish that the fact that X is 3 is a cause of phi. And I'm saying, well, think of but for. If X had a different value, then phi wouldn't have happened. So if you ignore the W part, just imagine this clause wasn't there. So this is just but for causality. It's saying if X were X prime instead of X, phi would be false. So if X 3 was something else, then phi wouldn't hold. That's exactly but for causality. If X hadn't had a different value, then phi would not have happened. Okay? But now I want to go beyond but for causality. And the way I'm going beyond but for causality is to say you can take and keep them fixed at their current value. Now, why does that matter? This is like an intervention. Because if you had changed X from being 3 to 5, that might have changed those other variables in W. But I'm saying, no. You can't change those variables. In other words, Susie and Billy throwing rocks. If Susie doesn't throw, then Billy's rock, under normal circumstances, would hit the bottle. But no, I'm saying, no, keep fixed the fact that Billy's rock didn't hit the bottle, which actually happened. So you have to fix the values of the variables in W to their actual values, what actually happened. And once you do that, you're going to get but for causality. This will make sense, I hope, once we see some examples. So that's the formal definition. If we keep you fix at their actual values, then changing X can change the outcome. So let me go back to the examples. Let's go back to the arsonists, where I don't need to worry about the W. I can take W to be empty. So in the conjunctive case, it's really easy. In the conjunctive case, I needed both guys to drop a match for the forest to burn down, because I needed both matches. So each one of the arsonists individually, but for causes according to the law, the forest wouldn't have burnt. Had arsonist 2 not dropped him, also, the forest wouldn't have burnt. Are we together? Okay. But just pointing out that an effect can have more than one cause. Sure, absolutely. Sure. Right. Right. So if I both punch him and kick him, oh, I see. This is existential. So there has to be something I can do, which is like, don't do anything. So this isn't saying anything I could switch it to would result in a different outcome. It just says there exists something I can switch it to. That say there is a set W of variables and there is a setting X prime. So it's existential quantification. And yes, indeed, it's possible that there's some other setting where it doesn't have any impact. Right. So, okay, the disjunctive scenario is a little more complicated because with disjunctive scenario, we don't have but for, at least not with one variable. If the first arsonist hadn't dropped the match, it would have been a fire because the second arsonist did. If the second arsonist didn't drop a match, there still would have been a fire because the first did. But if both arsonists don't drop matches, then there's no fire. So we would say that the fact that they both dropped a match, is what caused the fire, right? Let me keep going. Let me look at Susie and Billy. So now with Susie and Billy, it depends a little bit on the model. If you have a really naive model that just says, okay, my only variables are Susie throws and Billy throws and the bottle shatters, right? And what's the equation for the bottle shatters? If we're going to build into the model the fact that they never miss, then the bottle shatters if either one of them throws, right? So the equation for BS is just the disjunction. It's literally identical to the second arsonist model, isomorphic to technically, the disjunctive model, because it just says the bottle shatters if either one of them throws. Now, in that model, Billy and Susie play symmetric roles, and both of them are causes of the bottle shatter. But that doesn't capture our intuition. Now, what's wrong? This is just not a good model. In the actual model, Susie threw a little bit harder. Her rock got there first. This naive model is just not capturing that. So there's lots of ways of making the model more sophisticated. Let me give you one. But I want to capture the fact that it was Susie's rock that actually hit the bottle and shattered it, not Billy's. Okay, so here's one model, and it's not unique. But let me stress that I'm going to bake in the fact that Susie and Billy never miss. If they throw, they hit the ball. So I'm going to add two new variables, SH and BH for Susie's rock hits the bottle and Billy's rock hits the bottle, hits the intact bottle before it's been shattered. Now, because Susie throws a little bit harder or a little bit earlier, the equation for SH is Susie hits the bottle if she throws. So SH is 1 exactly if ST is 1. Susie hits if she throws. Now, on the other hand, Billy hits if he throws, he has to throw, but also Susie doesn't hit. So again, I'm going to bake into this model the fact that Susie hits, and if her rock hits the bottle, there's no bottle there for Billy to hit. So the equation for BH is true, BH is 1, if BT is 1, if Billy throws, and SH is 0, if Susie does not hit. That'll be the equation. Again, are we together? And finally, the same equation for BS, the bottle shatters if either one of them hits. Now, in that model, I claim, according to my definition, Susie is the cause, Billy is not. Why is Susie the cause? It's just what I said before. Let's fix Billy. In the actual world, in the actual context, Billy did not hit. Susie hit, Billy didn't. Let's intervene and clamp Billy. We fix that. If we change Susie from throwing to not throwing, the bottle doesn't shatter. We get but for causality. We fix Billy at not hitting. Right? So according to my definition, Susie's a cause. I can't, because in the actual world, Billy didn't hit. In the actual world, Susie did hit. If the bottle shatters, there's nothing I can do with Billy that'll change anything, right? They're not symmetric in this model because Susie hits and Billy doesn't. This is duh. Why is Susie a cause and not? Why is Billy not a cause? His rock didn't hit the bottle. Well, this model is rich enough to capture the duh moment, so to speak. Yeah. Well, I mean, there are different problems on them. Well, so all I can say is empirically, from the philosophy literature that have been various causality definitions, what the equations are. That means if you agree that or look at this in this case, if you agree that it takes matches two fires going for the forest to burn down, it's obvious what the equation should be. So at least let me say empirically, and this in other cases, no dispute about what it should be, and there's still a lot of dispute about what causality ought to be. Now, I agree in the real, I mean, let me not hide behind this. Well, for example, with cancer and smoking, it really is the case historically that people weren't sure if smoking caused cancer or if there was some genetic component that caused cancer and also caused just a different model. You have a gene, and so we see a correlation between smoking and cancer because the people who smoke have that setting of the gene, and they're also more likely to get cancer. But there's no causality between smoking and cancer. So these are just different models. They have very different equations. And there's real doubt, apparently, in the scientific community in the 40s as to which model was the correct, right? So there's no question there can be disagreements about what the model is. But it's questions. And we know scientifically, at least in principle, what kind of experiments have to be performed to check whether a model is correct. But even if we agree on the model, there was still an issue of, is A a cause of B given the model? So does that, I mean, just different. Neither is trivial. Rani. Yep. Yep. It's an existential quantification. They can be arbitrary. The only interesting W is a W that gets influenced. If W is not influenced by X, then you might as well ignore it. Yeah. Well, so it depends how you model it. Going to be, there'll be modeling that and disagree about the model. And depending on how you do it, you might get causality in one case, not in another. I mean, so that oh, that's okay. That is to say, although in some accounts in philosophy, there's a big distinction between action and non-action, that somehow some things are called actions and other things, I didn't do it, non-action, and only action can be causes. Here in my framework, there's no distinction whatsoever. They're just different variable, and no way of, X is 1 is did it, X is 0 you didn't do it. X is 0 can certainly be a cause. The fact you didn't do something absolutely can be a cause. There's no distinction between doing and not doing. At least the model doesn't recognize, there's nothing special about 1 versus 0. Well, so I'm looking at causality relative to a context, which is a fixing of the exogenous variables, yes. And I also allow in the definition fixing not just external variables, exogenous variables, but other variables. That's the W. In determining causality, I allow that. So I'm not sure I answer your question. Right. True. But I still would call you a cause because I'm allowed to fix the fact that they didn't. Right? That's what the W is. So my definition would say, in your example, that yes, the fact that you press the button makes you a cause, even though somebody pressed the button. That's a property of the definition, which I view as a feature. I actually want to call you a cause, but you don't like the definition. I see another question. No, there can be multiple causes. Definitely in the conjunctive case of the arsonists, where all it takes is one match, each of them separately is a cause. So you can definitely have multiple causes, right? The definition absolutely allows for A to be a cause of B, A prime to be a cause of B separately without A double prime to be a cause of B. We can definitely have multiple causes of an outcome. As the arsonist example is the conjunctive case, is such an example. One more, but then otherwise Raphael will yell at me for not finishing on time. Yep. Yep. Sure. That's true. But I just want to say that's not interesting. So let me explain. So it's certainly the case that you could say, look, just with but-for causality, if you had a richer model, Susie's throw cause of the shattering exactly at 10 o'clock. Because had Susie not thrown, Billy would have shattered at 10. And that's not interesting because we don't want those distinctions, such fine-grained distinctions. It'll also turn out that the fact that the wind was blowing at a certain strength is a cause of the bottle shattering at 10 o'clock, as if there hadn't been a wind, maybe Susie would have gotten there minus epsilon. So once you allow such fine-grained variation stopping you in a richer model, Susie would be a but-for cause. And the other problem is just doesn't the way people think about it, that they want level of granularity. So let me first say everything's relative to a model, and part of the model is choosing the variables. You're perfectly entitled. There's nothing I can do to stop you, for example, from choosing much richer variables that include things like the bottle shattered at 10, the bottle shattered at 10 plus epsilon, and so on. In that richer model, indeed, Susie would be a but-for cause. And I would just argue that people wouldn't find the richer model useful, at least in this case, for the kinds of talk about. So as a separate matter, we'd have to debate what's the most useful model for us. I mean, if for lawyers, we would debate about what's the right model, right? So I think there are good reasons not to choose your model. Because it's a quick one, because I just want to, yeah, otherwise I'll just never finish. I actually have a lot more to say. So let me give you some examples that maybe aren't so obvious. This is an example due to Ned Hall, who's a philosopher at Harvard. So Billy contracted, but he's treated on Monday, so he's fine on Tuesday. But had Monday's doctor forgotten to treat Billy, no problem. Tuesday's doctor would have treated him, and he would have been fine on Wednesday. You're fine the day after your treatment. However, there's a catch. This is a philosopher. If you get 2 doses of medication, if both Monday's doctor treat him and Tuesday's doctor treat him, then you die. Okay? So let me point out the fact that Tuesday's doctor did not treat Billy. So what happened is the right thing happened. Monday's doctor treated him. He was fine on Tuesday. Tuesday's doctor didn't treat him, so he didn't die. Right? So the fact that Tuesday's doctor didn't treat him is certainly a cause of him being alive, a but-for cause. If Tuesday's doctor had treated him, he'd be dead, given that Monday's doctor treated him. So look, I claim the causal model here, and so I'll know this is partly directed at you, that given the way I've told the story, there's no dispute about the causal model. We have variables, or a reasonable choice of variables is Monday's doctor treats him, yes or no. Tuesday's doctor treats him, yes or no. I'm going there's a causal link between Monday's doctor and Tuesday's doctor. Think, Monday's doctor writes in the chart, I treated him. Tuesday's doctor looks at the chart and doesn't treat him. So the equation is that Tuesday's doctor doesn't treat him if Monday's doctor does, and he does treat him if Monday's doctor doesn't, right? So we have an edge from Monday's doctor to Tuesday's doctor, and an edge from both of them to Billy's medical condition. And Billy's medical condition has 4 possible values. He's okay on Tuesday and Wednesday, which is what happens if Monday's doctor treats him and Tuesday's doctor doesn't. He's sick on Tuesday, okay on Wednesday. That's what happens if Monday's doctor doesn't treat him, but Tuesday's doctor does. He's sick both Tuesday and Wednesday. That's what happens if neither doctor treats him. And finally, he's okay on Tuesday and dead on Wednesday. And that's what happens if both doctors treat him. And that's the equations. I mean, I'm not going to write down the equations, but the equations literally say this, right? That Billy's medical condition has 4 possible values. Which of the values arises depends on what happens, whether or not Monday's doctor treats him and Tuesday's doctor treats him. So what can we say? Are we together? I mean, I claim this is completely straightforward to model, given the way I've told the story. So Monday's doctor treating him is a cause of Billy being okay Tuesday and Wednesday, but for cause. If Monday's doctor hadn't treated him, depending on what Tuesday's doctor does, he'd be sick on Tuesday, right? And Monday's doctor treating him is the cause of Tuesday's doctor not treating him. Again, I'm assuming I have an equation that says Tuesday's doctor treats him if and only if Monday's doesn't. But now, and then Tuesday's doctor not treating him is the cause of him being alive on Wednesday. Being alive is his medical condition is 0, 1, or 2, not 3. He's not dead. Okay, here's the kicker. Monday's doctor treating him is not a cause of him being alive, so we don't have transitivity. We have A being a cause of B, B being a cause of C, but A is not a cause of C. Okay. Now I'm going to talk. So we don't have transitivity, and now I'm going to be fast. And we have intuitions that causality should be transitive, but there's lots of examples like this that show that, yeah, often, typically it is, but not always. And we also have a property, right weakening, that says if A is a cause of B, B implies B prime, A might not be a cause of B prime. Let me just keep going because there's a lot more things that I wanted to say, and I'm obviously running out of time. This definition does not take into account issues of normality. So here's a story. The receptionist in the philosophy department keeps her desk stocked with pens. The administrative assistants are allowed to take pens, but faculty members are supposed to buy their own. In practice, both assistants and faculty members take the pens. She started out with 2 pens. A faculty member took a pen and an administrative assistant took a pen, but there's a rule that says faculty members are supposed to buy their own pens. So if you ask people who's the cause of there not being a pen, when the next person wants to come and take a pen, almost everybody says it's the professor. And Kahneman and Tversky, this is Danny Kahneman who won a Nobel Prize, they actually worked on, there's a paper by Kahneman and Miller, came after the Kahneman-Tversky paper, that event is more likely to be undone by altering exceptional rather than routine aspects of the causal chain that led to it. And roughly in our language, this is saying that if you're going to call something a cause, if you have a choice of multiple causes, you look at the one that the counterfactual makes things more normal. Let me explain. In the case of, if you want to blame the faculty member, if you take it to make the world more normal, because they're not supposed to take pens, compared to the admin not taking a pen. So we can extend our model to deal with that. And given the time, I won't go into details, but once you add normality, you get a more refined definition. And now I wanted to say one other thing before they kicked me out. Responsibility and blame, this is where we add probability. So if you have a vote, let's say 11-0, that feels different from 6-5. In an 11-0 vote, let's say, okay, each of the voters for something is a cause of the outcome, but their responsibility is the 5 vote. How do we capture that? So we have a notion of responsibility that more or less says, what's the degree of, what is a number between 0 and 1? It's not a probability. And roughly your degree of responsibility is how many things have to change before you're a cause. You're not going to be a direct cause. You're not going to be critical unless 5 people flip their vote. Then it'll be 6-5. You're going to be critical. So your degree of responsibility is 5 plus 1. That's very naive, 1/6. Whereas in the case of the 6-5 vote, you're already critical. Your degree of responsibility is 1. Turns out this notion, despite being naive, this naive notion captures a lot of things that people care about. I'll talk about that in a second, I hope. All right, so all I can say is we have a notion of blame. We talk about probability, we talk degree of responsibility, and that turns out to be interesting in the case of firing squad. To what extent are you to blame if there are 10 people trying to fire at you and only one has a live bullet? And then I would have talked about how this is relevant to computer science, but apparently I'm not going to be able to.